So the first problem that they listed really has nothing to do with E1. Thanks a lot, QBank. But number 2A talks about the quantization of electron orbital angular momentum, which is E1. So let's proceed from there. So reading over the question, it seems that just AI and AII are part of E1. And so it says, in the Bohr model for hydrogen, orbital angular momentum is quantized. So MVR, that's orbital angular momentum. So it's the MVR. And then it says, outline the effect this has on the electron energy. I think that's a really weird question, but basically what they're getting at is that the angular momentum is quantized, but the energy is also quantized, and we can see that in the equation E equals negative 13.6 eV over n squared, that the energy is in quantities of 13.6 EVs, that the energy can't just be continuous. All right, so AII for the hydrogen atom orbit radius in the n equals 2 is 4 times larger than orbit radius in n equals 1. Find the ratio of the speeds 2 to 1 or the two electrons. So they had a different couple approaches that they would use. I would say use of the quantization condition. Why can't I speak today? So and the formula they're using right there is the angular momentum, MVR equals NH over 2 pi. So therefore the speed of the electron is NH over 2 pi mr. So the two different electrons in the two different energy levels are going to have the same mass. N is going to be different, and R is going to be different. So let's take a look. So that's for the level 2, n equals 2. It said the radius is 4 times that for the n equals 1 state. And of course, a lot of this stuff cancels out. We can get rid of the h, the 2 pi, and the m. And that gets us 2 over 4 over 1 over 1, which is just 2 over 4, which is 1 half. And that's what they get. They get it here 1 half, they get it here 1 half. And then if we track this method, we also get it here 1 half. So yeah, 1 half is the way it goes. That's the way I would do it, considering that you're talking about speeds, and that's the equation that has electron speed in it. So I don't know why they consider that the third alternate. That would be my first choice. All right, and so yeah, we're not going to worry about B, since it's not part of the new syllabus. We're not going to worry about C. It's not part of the new syllabus. And so now we're on number 3, which of course starts at the bottom of the page, because Question Bank is loving these bizarro page breaks. So I'm going to do this up here. I'm going to say 3. All right, we'll go from there. One of the nice things about paper 2 is that sometimes when you look at the mark scheme, the answer is right there, and you don't really have to say much more than that. I think this one's interesting in that it's 2 marks, but really the 2 marks are the same thing. It says, explain how elements present in the sun, or any star for that matter, are identified, and it says mention of spectral lines. But then what about those spectral lines? The fact that the spectral lines are specific for each element. If it were up to me, I would say that the first mark would be that the spectral lines are specific for each element, but then also the way that they say, well, how do you know that the spectral lines represent an element? Actually, as I'm writing this, I think spectral lines are compared to known samples, and come to think of it, spectral lines from the sun, the reason why helium is called helium is because helios means the sun. It's a Greek word for sun. And so they discovered the spectral lines for helium in the sun before they discovered that helium itself has spectral lines. Like, if they got a sample of helium on Earth and they compared the spectral lines and they were like, oh, hey, it's the same as the stuff on the sun. I'm going to look into that. I'm going to look into that right now. Based on my reading, it seems that spectral lines in stars and spectral lines in samples on Earth were kind of being investigated roughly at the same time. Anyway, but that is 3A. Okay. Okay, and we don't need to worry about 3b. We don't need to worry about 3c. These are not E1 topics. Same thing for 3D, that's astrophysics. And so really only 3a is relevant to topic E1. Okay, so now we have number 4, which again is they broke the question strangely. 4, the table shows some of the energy levels for hydrogen. And so we have our ionized state, excited states, and ground states with the relative energy, and energy of states is measured relative to the ionized state. They say n equals infinity for ionized state because the electron is not actually bound by the energy levels, it is ionized, it has left. So 4A and B are, I think, more SL things, but they're worth kind of like looking at. So 4A, one difference between atom in excited state and atom in an ionized state. Excited state, electron bound to the atom, and then the ionized state means the electron is not bound to the atom. I pretty much just said that in discussing the table. So that's 4A. And in B, how is electromagnetic radiation emitted from a hydrogen atom in an excited state? The electron falls down to a lower state and emits a photon. And then C says radiation of wavelength 6.6 times 10 to the negative 7 is incident on cold hydrogen gas. Some of it's absorbed by the gas. What is the region of the electromagnetic spectrum? Look it up on the spectrum chart. It's visible light. And then CII, determine initial and final states of the hydrogen atom that are involved in its absorption. And so you do that by E equals hc over lambda, and you get 3 times 10 to the negative 19 joules, and then convert to EVs because the chart that it's giving you is in EVs. And then since we're converting to EVs because the chart's in EVs, and then we wind up getting 1.88 or 1.89 EVs, but that's the change in energy. And if that's the change in energy, you got to figure out, based on the chart, which levels will get us 1.89 EVs. And it's not from 3 to the ionization level or from 1 to 2, but from 2 to 3, that's 1 point. That's, you can check it out, but that's 1.89 EVs. So, and it says it absorbed the light, right? Light is absorbed by the gas, so it's going from 2 up to a higher level, from 2 to 3, if it's absorbing it. So transition is from 2 to 3. Now, that's all relevant to the topic we're studying, but that's all SL content. So, like, I would say number 4, so that's all relevant to E1, but it's SL content. And then, thank you, question bank. Number 5 is a repeat of number 4. It is literally the exact same question. So we don't need that. And then, let's see, number 6. And then for number 6, A has to do with the photoelectric effect. And so that's actually going to be our next topic, but it's not E1. So we're not going to worry about A. But then B talks about distance of closest approach. That is a thing that we're working with. I don't know if there's some kind of other description for B, but there's enough information to solve for BI, so let's go. Let's actually do something rather than cross problems out. Alright, so BI, it says the charges are 2e for the alpha particle and 82e for the lead. And the distance of closest approach, again, reminding on how that works. Okay, so then they work the numbers through. There's one thing I want to note here, though. The 8.99 times 10 to the 9, that right there, the units are Newton meters squared per Coulomb squared. And then they set everything up in terms of elementary charges, which is fine. The Coulomb conversion cancels in the numerator and denominator, except that E shows up twice in the numerator. So one thing they are not showing is they need to include the 1.6 times 10 to the negative 19 coulombs per elementary charge in order to cancel the coulombs and the Newton meter squared per coulomb squared. So like technically this E drops out and this E drops out, but this guy does not drop out, so you have to include this guy as well. So when you do 8.99 times 10 to the 9 times 2 times 82 times 1.6 times 10 to the negative 19 divided by 5.9 times 10 to the 6, that's when you get 3.998 times 10 to the negative 14. So just be aware of that. So that's, and then let's see, they reduced it to one significant figure. Why did they do that? Oh, show that the distance is about 4 times 10 to the negative 14 meters. Well, there you go. And I really like this BII. This is important stuff. So it says the radius of the lead nucleus is 7.1 times 10 to the negative 7 meters. Why will there be no deviations from Rutherford scattering in the experiment in BI? And it's like, well, why would there be deviations from Rutherford scattering if there are other forces in play? So deviations from Rutherford scattering, other forces. So check out the mark scheme. Mark scheme says Costa's approach is significantly larger, way bigger than the radius of the nucleus. So in other words, it's far away from the nucleus, right? Therefore, the strong nuclear force of the nucleus will not act on the alpha particle. And it's like, well, why would it act on the alpha particle? Alpha particle is 2 protons and 2 neutrons, right? So those are nucleons. If that alpha particle rolls up on the nucleus and gets too close, gets within the range of the nuclear strong force, then the nuclear strong force will mess with the alpha particle and will actually deviate from Rutherford scattering. So that right there, that's pretty cool. That's important stuff. Okay, let's move on. So here's number 7, talking about de Broglie wavelength, and where the equation for de Broglie wavelength is given. And they take an electron beam and they shine the electron beam at a sample of carbon-12, and then find that based on the intensity of the electrons versus angle, there seems to be a there seems to be a dip, and it's kind of like you may not recognize this graph, but I realized later on in BII that they were talking about single slit diffraction, and this graph is actually 1/2 of the classic diffraction pattern. And so basically it's like this graph here kind of goes like this, and here's the minimum and there's the other maximum as it goes. So that's the minimum caused by the diffraction envelope. And so 7a says show wavelength is 3 times 10 to negative 15 meters. I mean, basically you just wind up using this equation that they gave you. We have H, we have C, we have the energy in electron volts that you convert to joules in order for that to be appropriate, to get the correct units. For H, for using H, and you wind up with 2.96 times 10 to the negative 15 meters, and that's going to be relevant later, but that's the wavelength. Okay, great. Then it says, discuss how the resulted experiments provides evidence for matter waves, and it says it shows that it goes diffraction and only waves diffract, right? 2 marks there. And the diffraction, how do I know about the diffraction? Again, going back to this graph, it's not a great illustration, but it is half of the diffraction pattern that you get from single slit diffraction, the diffraction envelope. So it's the graph. Or even the fact that there's a minimum shows that destructive interference is happening, and interference happens with waves, not with particles. Fine. Now, all of these things, none of this is EI, right? Or E1, or whatever you want to call it. Sorry, E1, right? Then BII says the value for the diameter of the carbon-12 nucleus is 4.94 times 10 to the negative 15 meters. What's the angle that the minimum is formed? And that's actually single slit, which I think is a very interesting application of single slit. It's not a slit, but it's still diffracting around that single object being the nucleus of the carbon-12. Yeah, 12. a nucleus of the carbon-12, diffracting around that single object, you still wind up with a single object slash slit diffraction pattern. So we can use that formula, theta is lambda over b. And so that's where it's getting the 2.96 times 10 to the negative 15 over 4.94 times 10 to the negative 15, and to figure out the angle. And then B triple I says why electrons with energy of approximately 10 to the 7 electron volts would be unsuitable for the investigation, because if you convert that electron volts to joules and do lambda equals hc over E, you wind up with a wavelength that is much bigger than the nucleus. And so if your wavelength is bigger than the nucleus, you're not going to get that much diffraction effect. You're not going to be able to measure the effects. So yeah, the diffraction effects are not going to be measurable, really, if theta is much bigger than B. But again, we're not in EI land yet. But C, 7C, experiments with many nuclei suggested the radius of the nucleus is proportional to A to the 1/3, where A is the number of nucleons in a nucleus, show that the density of a nucleus remains approximately the same for all nuclei. And so we have radius of a nucleon is Fermi radius times the nucleon number to the 1/3. We know that density is mass over volume. Density is the mass of a nucleon times the atomic number, I should say, it's the mass of the nucleon times A times the number of nucleons you have over the volume of a sphere, 4/3 pi r cubed. But r is Fermi radius a to the 1/3, and so basically r cubed and the a to the 1/3 just wind up with a, and the two a's cancel. And so that shows that the density of a nucleus remains approximately the same for all nuclei, showing that density does not depend on A, the nucleon number. So that's C right there. And that's number 7. So our final question is number 8. It says, to determine radius of carbon-12 beam of neutrons scattered by a thin film of carbon-12. Graph shows variation of intensity with scattering angle. De Broglie wavelength of the neutrons is 1.6 times 10 to the negative 15 meters. All right, well, let's look at the graph. All right, shows that there's a dip at 17 degrees. And again, it's showing a portion of the full diffraction pattern. There's that diffraction envelope, right? And then they mention a bunch of stuff about copper. Okay, pure sample of copper 64 is a mass of 28 milligrams, and the decay constant of copper 64 is 55 times 10 to the negative 2 decays per hour. And then de Broglie wavelength, I think that's later in topic E. It says, not consistent with Bohr's conclusion that the electron's orbit in a hydrogen atom has a well-defined radius. Bohr had the right idea in that the electron should be in a certain spot, but a well-defined radius is not how we know it to be. And so the de Broglie hypothesis says that the electron is represented by a wave. And if it doesn't have a definite position, and we now know from Schrodinger, the electron position is more like a probability cloud, like in a particular area, boop, there's the bell. In a particular area, you're more likely to find an electron, and in other areas, not so much. So no, it's not well defined because the electron has a wavelength and functions as a wave at that energy. So 8b, I should say, or BI. Estimate using the graph the radius of the carbon-12 nucleus. So this is just like 7b double I, where theta is lambda over b because of the diffraction, and b is the size of the nucleus, lambda is the wavelength, and theta is the angle. The wavelength is given back here, 1.6 times 10 to the negative 15 meters. There's lambda. So that right there, it's right there, 1.6 times 10 to the negative 15. That's lambda. And then the angle is taken from the graph up here, where we have our minimum at 17 degrees. That's where the 17 comes from. And so and it says sine, but for small angles, theta and sine theta are similar, but you can throw in the angle and the wavelength, and you can solve for the size, which you get 5.47 times 10 to the negative 15 meters, but it says radius, be careful, read carefully. So this right here, this size, nucleus size, not nucleon, nucleus size. But as for the radius, so you want to divide that by 2, and you get 2.7 or 2.8 times 10 to the negative 15 meters. But again, I wouldn't call that E1 per se, but it is a good diffraction question that we've done before. But anyway, let's take a look at B double I, which does have to do with topic E. Ratio, volume of a nucleus, they spelled nucleus wrong. Volume of a nucleus of mass number A divided by the volume of a single nucleon is approximately A. And it's like, what does that have to do with by reference to the strong nuclear force? It says it implies that the nucleons are very tightly packed. So it's kind of like if you have a nucleus of mass number A, say it's like 10 nucleons, or 7. 7 makes a nice tight pack. And if they're kind of close together, then it's like the volume of a nucleus of mass number A, this would be 7 in this case, divided by the volume of one nucleon is going to be the number of particles that you have. In other words, there's very little space between the nucleons. And if there's very little space, that means that they attract each other very strongly, so the nuclear force is very strong, a very strong attraction. And then finally, Ci and C double I is not E1. It has to do with radioactivity. I believe that's E3. So we're not going to worry about that right now. And that was the last question.